So we finished the differential method, and just a quick remind, if you don't have any idea what is the reaction order for your interesting chemical equations, probably and also you recheck, you already revise reaction order is not equals to 1, so you can use the half-life time to get a reaction order. But the other method we are going to show you or introduce to you will be we call the integral method. So the integral method is we need to derive the particular form of rate equation for zero order, first order, and second order. As long as you get the particular form, then you can input all your data inside to see whether it fits to this rate equation or not. Then you have a chance to know is your chemical equation belongs to first, second, or zero order. So as I mentioned, so following several slides, I'm going to show you how to derive a particular form of rate equation for first, second, and zero order of rate equation. So let's move to the first order reaction. So what we have here is we have irreversible unimolecular type first order reactions. So we consider the reaction A and decompose or generate our product, and this belongs to first order rate equations. So you can write down the consumption rate of reactant A equals to minus dCA over dt and equals to kCA to 1. So you just simply move the Ca to left-hand side, dt to right-hand side, and take the integral on both sides. And for the time, you integral from 0 to t. From the concentration of reactants, you integral from Ca0 to Ca. Then you will get this rate equation in terms of Ca and T. So if your reaction belongs to first order reactions, for sure, when you use this as a y-axis and T as an x-axis, and when you input all the data, means you input the Ca at a specific time point, and you input several data, and you try to plot the y versus x axis, then you will get the straight line, and the slope will be equals to rate constant k. Okay? But this is the expression is in terms of Ca, concentration of reactant A, and time. But in most of cases, people will use the term we call a fractional conversion. So fractional conversion means fractional conversion Xa equals to 1 minus Ca over Ca0. You use 1 to minus the remaining of reactant A. The fraction of remaining of reactant A means how much fraction of reactant A be converted to product. So in this case, we use the Xa. And we also take the deviated with this equation, and the Ca0 is a constant, so we got the dxa minus dCA over Ca0. So next, I'm going to try to convert these equations in terms of Xa versus time. So how to do that? So I just directly divided by Ca0 together. So we will get a minus Ra divided by Ca0. And this part will be minus dCA over Ca0, right? The minus dCA over Ca0, so you will get the dxa divided by dt. And this kCa divided by Ca0, so you can leave k here, and Ca divided Ca0, you will get 1 minus Xa, put here. So now you can focus on these equations. simply just move 1 minus xa to the left-hand side, dt to right-hand side, and take the integral for both sides. And also, the time is integral from 0 to t, and xa will be starting from 0 to xa. Don't forget, this is a fractional conversion. In the beginning, there's no any reactants be converted to product, so it will be x to x, 0 to xa. So you will get these equations. So as long as you plot this log 1 minus xa as a y-axis and t as a x-axis, and you input the xa at specific time point, then if you get a straight line, then that will say your reaction order belongs to first order reaction. So based on this information, you can combine this one with the half-life time analyze, right? Because when you try to use the half-life time analyze method, you need to make sure your reaction is not belong to first order reaction. So you need to check by using this. You need to check whether your reaction belongs to first order by using this, right? These results. As long as you know it's not, then you can use the half-life time analyze to analyze your reaction order and the rate constant. So this is easy. This is the first order reaction. Let's move to the irreversible by molecular type second order reaction. So the reaction, what we have here is it is an elementary reaction, and A react with B and generate products, and it is a second order reaction. So when we try to write down the rate equation, can express like this: minus consumption rate of reactant A equals to minus dCA over dt. And because we use 1 mole of A react with 1 mole of B, so the consumption rate of A will be equals to consumption rate of reactant B, and will be equals to KCA to 1 and CB to 1. So 1 plus 1, so total reaction order will be second order reaction. And don't forget, our purpose actually is express this rate equation in terms of xa and t. So next I'm going to do some substitution. Substitute the ca and cb in terms of xa. Okay, so what's the ca? Ca can be expressed equals to the before reaction happens, so it's a ca0 minus the ca0 times the xa. xa times the ca0 means the fractional conversion of reactant A, right? So you minus the reacted portion is the remaining of reactant A, okay? And when you try to write down the CB, can also is CB0 before reaction happens. So the concentration of reactant B, we call it CB0. And we minus this portion because you consume 1 mole of A, you will react with 1 mole of B, right? So the reacted portion can be expressed like this. I use this to represent the reacted portion, right? It will be the same for A and B. And next, don't forget, I want to rewrite this equation in terms of xa and t. So minus dca will be equals to ca0 dxa y minus dca here will be equals to dxa ca0 and this part actually I will use this term to substitute ca and this term to substitute cb. Then after arrangement I can get this reaction, the rate equation. And here, please take a look on here. Yes, you got the parameters xa and t, everything, and the rest of part are the constant. For example, like the ca0, K and CB0 and CA0. But interesting part is what's the CB0 divided by CA0? Actually, it's the initial concentration ratio of reactant molecular B to A, right? So based on this, in order to get the XA as a function, the rate equation in terms of X and T, you can simply divide this rate equation into two parts. The first part is while m not equals to 1, which means in the beginning, the initial concentration of CB and CB0 and CA0 is not the same. So the first case will be while m not equals to 1. If m not equals to 1, so you can, in order to get that, you need to move this term to a left-handed side and dt to right-handed side and get the integral on both sides. So CA you can drop it, so you left over CA0 to 1. You need to solve this integral equation. And the second case, probably m equals to 1, so you got the x minus 1 minus xa, 1 minus xa, so you got the 1 minus xa to 2. Okay? Sorry. So after you already listed two equations, right? And then you try to solve this two equations. So for first one, you will get this expression in terms of XA, XB, in terms of and T, and while m not equals to 1. So in this case, if you put this as a y and this is T as a x, if your equation belongs to second order reactions and initial concentration of reactants are not the same, then you should get the straight line. And the slope will be equals to k times CB0 minus CA0. And the detailed deviation from here to this, you can check here. I upload my handwritings. You just separate this part into two terms and integral individually, and after some arrangement, then you can get finally you can get the results. Okay, you can take a look for this one. So regarding to the while m equals to 1, it's quite simple, right? You just need to, this is dt, you just need to integral this term, so you will get these results. So when you use this as a y and this as a t, then you put all the xa as a function of t, xa at specific time point, then you should get a straight line and the slope belongs to k. So if it is, then your chemical reaction belongs to second order reaction. Okay? Okay, so let's move to the last one. You already get the particular form of rate equation for second order, right? And while m not equals to 1 and m equals to 1. And also for the first order, you also get the particular form, right? So now we move to the last one, is the zero order reaction. The zero order reaction means the consumption rate of reactant A equals to K, nothing related to the concentration of reactant A. So based on this, I just move to the dt to right-handed side and take the integral from T from 0 to T and the concentration from CA0 to CA. So we will get this expression. And also I want to express this in terms of XA, so I can write this down. CA0 minus CA is the fractional conversion of reactants. So you got the XA, CA0 equals to KT. So when you try to write down the CA as a function of T, this is a Y, this is X, so the slope will be, this is a X, so the slope will be minus K. And if you try to write down this is a Y and this is X, so the slope will be K divided by CA0. Okay, so this is the zero order reaction, but most of people will ask, Professor, what's the in what kind of conditions your reaction will belongs to zero order reaction? I believe you guys know what's a zero order, right? Zero order means the nothing related to the concentration. The order is zero. Okay, so like a Ca to 0. So in what kind of conditions? So there are two general conditions belongs to zero order reactions. The first one is we call only a small fraction of reactant molecules in a specific location can able to react, and this fraction is continually replenished from a larger pool. So in this case, what this means, but before we explain this one, you can see the second condition. When two or more reactants are involved, the concentration of some are much greater than those of others. It's similar idea, right? So what this means? So I'm going to give you this example. It's a decomposition of nitrous oxide. So we have a nitrous oxide, and this is a decomposition reactions. It will decompose into a nitrogen and oxygen. And the temperature should be around 575 degrees. So if you want to decompose the nitrous oxide at a lower temperature, then probably one way you can do is you can put in the catalyst. So the catalyst for nitrous decomposition can be a hot platinum wire, which can serve a catalyst. So the reaction will be belongs to zero order. Why? So I will explain this by using these figures. So we have a hot platinum wire here, and surrounding we have a lot of nitrous oxide. But this is a catalyst, right? And catalyst can help on the decomposition of nitrous oxide at lower temperature, but only for the nitrous oxide adsorbed on the platinum wire. So even there's a lot of amount of nitrous oxide, but only this tiny fraction of nitrous oxide adsorbed on the platinum wire can be decomposed into nitrogen and oxide. As long as this full or few nitrous oxide decomposed, then probably they will continually to decompose. There are continual more nitrous oxide adsorbed on the platinum wire. So in this case, only small fraction of reactant molecules of nitrous oxide on platinum can be decomposed. Okay, so this is what we call. So based on this, only small fraction of nitrous oxide can be decomposed. So this chemical reaction, the rate equation, is nothing related with the real concentration of nitrous oxide. So I'm going to end the integral method by using two examples. The first one is this one. The reactions of the sulfuric acid with diethyl sulfate, and we can generate this product. And here the question tells you we have the same initial concentration of these reactants, and you also can record it the concentration of product as a function of time from time 0 to infinite. Then I can record the concentration of product. And the question here is, can you reconstruct the rate equation for these chemical equations? And here your questions also tell you force you to use the integral method. So in this case, all the integral, but because we need to use the integral method, so the particular form I derive for 0, first and second order will be the expressed in terms of XA, fractional conversion, as a function of time. So, but here we don't have XA, right? So I just want to remind you, just a remark, initial concentration m equals to 1, okay? So here, we want to write down the fractional conversion can be expressed equals to 1 minus Ca over Ca0. So my question would be, how to get the XA? Here, we, instead of recorded concentration of reactant A, we recorded concentration of product. So can we do some, are there any relationship between Ca and Cr? Okay, so I will try to write down. So here you can equals to Ca0, upper portion will be Ca0 minus Ca. What's the Ca0 minus Ca? Is the, and this is a Ca0 minus Ca is this part already be generate the product, right? So you consume 1 mole of reactants, you will generate 2 mole of product. So this can be write down as a Cr divided by 2 here. Because Ca0 minus Ca, this part already to generate a product, but you consume 1, you will generate 2 product. So you will should be write down Cr divided by 2. Okay, based on this, I already we know the Cr at specific time point. So I know the, in order to know the XA as a function of time, I need to know the Cr as a function of time. But still, one information I don't know is Ca0. So do you know what's the Ca0? Means the concentration of reactant A before reaction happens. So when you check here, the infinity means when the time reach to infinite, then can be considered the total reaction. The reaction already be completely, right? Complete. So the Cr you got a 5.8. So you got the Ca0 should be 2.9 divided by 2. So based on this, we already know this one and also Cr. So you can get the XA as a function of time expressed like this. Then as long as you got the XA as a function of time, then you can input this data into the particular form for 0 order, first order, and second order. So I just write down the rate equation in terms of XA and T. So based on this, I have the XA as specific time point. So I use this as a Y, this as a X. If it is a 0 order reaction, the data should be like a straight line, right? But it is not, so it's not the 0 order. And if it is first order, so if when I input the XA here and at specific time point, I use this as a Y and this is a X, should be also a straight line, and the slope will be belongs to K, and it looks like a straight line, so the slope is corresponding to K, rate constant. And still I want to recheck whether it belongs to second order reaction. So what I do is I also input the XA here and use this as a Y-axis and this is X-axis. Then I try to plot this figure, and if it is straight line, then it belongs to second order rate equation, but it is not, right? So after testing, so I'm convinced myself that these reactions belongs to first order rate equations. And don't forget, yes, it is first order reactions, And don't forget the slope is k, right? So when I ask you to reconstruct the rate equation, you need to input the value of k and also the reaction order, okay, to reconstruct the rate equation. And next, this is a last example I hope you can try to practice here. This is I have a decomposition process for the liquid A. So means the liquid A will decompose to product, and this is an irreversible process. And as I know, 50% of A is converted to product in 5 minutes. And how much longer will it take to reach 75% conversion? So my question will be 50% of A is converted to product, means XA equals to 0.5. This is quite important. And it takes 5 minutes. And how much time it takes when this reach to 75% of conversion? 75% of conversion means XA equals to 0.75. And what's the time? So because the question didn't tell you the reaction order, so under this this question gives you some hint. For example, like could you tell us how much longer if this belongs to zero order, first order, and second order? So you need to calculate each of them. And if I highlight, please derive the equation. So you need to start from the details like this, and get the deviation to show the rate equation in terms of XA and T. Okay, so directly use this term relationship and put all this data inside, and you will get it's around 77.5 minutes. And for the first order reaction, you need to formulate this one and move this list to the left hand side, dt to the right hand side, and take the integral. Then you will get and also if I ask you to express this rate equation in terms of XA and T, then you need to divide it by CA0 together, right? When you divide with CA0 together, then you can get this relationship. Then you also you can input the 0.5 and 5 minutes here, and 0.75 and it's X, so you got the 10 minutes. And for the second order reaction, I can, even though the question didn't mention anything, but in this case I can assume m equals to 1. So under this case I can calculate it's around 15 minutes. Okay, so just